Today, I'm going to talk about programming essentials and cover some of the key understandings and mindsets you need to write good code. The first coding concept I want to discuss is what I call leverage. And what I mean by this is that whenever possible, try to avoid writing any code at all. So in the community of practice, if your team decides it wants to write some code to import an Eclipse data file into a Python data frame, before you do anything else, have a good look around on Google and see if this code or utility has already been written by somebody else. Don't reinvent the wheel. There may well already be some good code you can leverage on the internet. Another aspect of leverage is that quite often, when you do have to write some code, you don't have to start with a blank page. One of the big advantages of Python is that there are a vast number of pre-written libraries that you can easily import into your project and use to give your coding a head start. You can find libraries like this again on Google, a website called Stack Overflow, or take a look at pypy.org. That's pypi.org. When you find some similar code to what you want on the internet, it's easy to tell what libraries are being used in that code because by convention, the imported libraries are normally the first lines of a Python program. Look for the words import or from import. As your coding gets better, you will also come across frameworks which extend the idea of libraries to be even more encompassing of everything you need to achieve a particular task. For example, Django, spelt D-J-A-N-G-O, is a complete web application framework that allows you to build dynamic websites. Some of the biggest websites in the world, like Instagram, are built using these Python frameworks. The next concept of coding is a straightforward one. It's the concept of sequence. All computer programs at some level are a sequential list of tasks that need to be executed. Each line is executed one after the other from top to bottom unless there is a loop or a jump in the code which you can easily see. The third concept for you to understand is that of branching. In a particular piece of code, quite often you need to do different things depending upon the circumstances. For example, if I was writing some code that would process all the Excel files in a particular directory, I would probably need the code to consider each file in the directory in turn and then decide if this file is an Excel file. If it is, then it should be processed, or otherwise, in this case, do nothing and just move to the next file. So the way you do this in most programming languages, including Python, is to use the if statement. If the answer to a particular question is true, then do something, and if it's not true, do something else, or do nothing at all. This something different is identified by the else keyword. So it says if this, do this, else do something different. A real-world example would be if my fridge is not empty, then get a bottle of beer out of the fridge and drink it. Else go to the bottle shop, buy beer and put it in my fridge. This is an if then else statement. And in coding, it's a fundamental construct which you need to get very familiar with. Sometimes you may have seen something similar in Excel with the Excel if statement and also VBA. If statements can also be nested, so you can have an if statement inside another if statement. So for example, you might say, if it's Monday, say Monday through the speaker. Else, if it's Tuesday, say Tuesday through the speaker. Else, if it's Wednesday, etc., etc. So you can have lots of if statements. In Python, this else if syntax is concatenated just to elif, E-L-I-F.
Here's an example of an if statement. This effectively says if in this simulation run the mode setting is IPR mode, then you execute this command. In this particular case, there's also an else if. So if it's not the IPR mode, check to see if it's the choke mode, and if it's the choke mode, do something different.
The fourth coding concept which you need to understand is looping. Often in computer programs you need to do something again and again. For example, when you're reading a CSV file into memory, you need to open the file and then read the file line by line until you get to the end. Conceptually, there are two types of loops. The first type is where you know in advance exactly how many times you want the loop to repeat. This is called a fixed iteration loop, and in most languages it's called a for loop, and in Python it is as well. So for example, if I was writing some software to ask people to scan their fingerprints on a fingerprint scanner one at a time, you might want a for loop to go through the code 10 times. In this example, the loop needs some kind of counter that would count from 1 to 10, so a full statement will be something like, for counter equals 1 to 10, do place your finger on the scanner and then remove. And then it would loop again, and it would go through all the fingers on your hand. So this is an example of a fixed iteration loop, also called a for loop. Another example might be a loop that iterates through every row in a Pandas data frame or Excel workbook.
Here we have an example of a for loop. What this is saying is effectively I have a list of wells, and it's saying loop through all of the wells in that range from well 0, which is just where it starts, through to the maximum well number, and loop through all this code here that many times. Although it's not explicitly said here to loop through 8 wells, what this is doing is it's still a fixed iteration loop, because the end well row variable there is a fixed number, so it does actually know how many times it has to iterate.
A second type of loop is where you don't know how many times a particular piece of code needs to loop, but rather you want to continue looping until such time as a particular condition is met. This is called a while loop. Let's say a piece of code needs to double a particular number until such time as that number is greater than 1,000. To do this, you would create a loop that says, wherever the number is less than 1,000, multiply it by 2. So for example, let's say the variable a was equal to 125. The loop would say, is 125 less than 1,000? Yes, it is less than 1,000, so loop again, multiply 125 by 2. Then it would say, okay, is 250 less than 1,000? Yes, it is. So therefore it would loop again. And it would say, okay, is the variable a less than 1,000? Yes, it still is, it's 500. And then it will keep going until it says, it doubles 500 again to 1,000, and it would say, is 1,000 less than 1,000? Well, the answer there is no, it's actually equal to 1,000. In this case, the loop would stop looping, and it would then continue on to the next statement. So this second type of loop is called a while loop. Keep looping until a condition is met, and then stop. Although the while loop is more powerful than the for loop because you can do more complex looping, it's also dangerous. It comes with risks. The while loop can lead to the dreaded infinite loop, where a piece of program code gets stuck in a loop that continues again and again and again forever, and it never exits. This is usually due to some kind of logic error, or because the input variables to the loop are not as expected. So in general, it's better to choose the fixed iteration loop, the for loop, for your jobs if at all you can. If you can't, go to the while, but think carefully about how the code's executing to make sure that it does actually exit.
So here's an example of some code. If you look up here at the top, there's some import statements. So this is importing the NumPy module, the pandas model, the datetime model, the time model. And then this one here is not importing the entire library norm, it's just importing a particular part from that library called SciPy stats. So that's an example of how to leverage external libraries.
Loops, of course, can be put inside another loop. So in computer science, this is called nesting a loop. For example, in a Pandas data frame or Excel workbook, you might want to process every cell. In this case, you would create a loop that goes through every row in the Excel spreadsheet, And then you'd also create another loop inside of it that goes across every row. So it would start off on row 1 and it would go through all the columns. Then that loop would finish and it would go to the second, back to the original loop and go to the second row, and it would process all the cells of there. And it would keep going until it's completed. The fifth coding concept we're going to introduce is the concept of functions. Whenever you're writing code and you realize that you've written this exact same thing before earlier, either in the same program or in a previous program, you need to think to yourself whether you're coding smartly. There is a saying in programming circles which is "don't repeat yourself," which people term dry. And what this means is, if you find that you're writing a similar piece of code again and again in your program, you probably should get that portion of code and put it into a reusable function that you can use every time you want it. This is a great idea because not only does it make your code more compact, but it also means that if you discover that your code has an error or is wrong somehow, you don't have to fix that code again and again in all the places where it exists. You just fix it one time in the function and then you've repaired the error. The sixth and final concept I'm going to introduce in this lesson is the concept of single responsibility, or as I like to call it, small is beautiful. While it's possible to code anything you want from start to finish, in 100,000 lines of code, a better way is to break the code into small chunks and solve them, and then try and create small, useful, reusable bits of code. To get the entire complicated program to work, you just string together these smaller bits and you get the same outcome. This is absolutely aligned with the maxim to not repeat yourself, and it's also consistent with the concept of leverage. If you write it once well, you can reuse it again and again, not just in this program, but in the next one that you do. You don't want to be writing a new program from scratch every single time. Instead, you want to leverage other people's code, or you want to leverage your own code from previous projects. A great way of doing this is to keep your programs small, and when you want to do more complex programs or workflows, you just combine them. What you find is that over time you create a whole library of little bits of code that you can reuse, and slowly but surely all the programs you want to write become easier and easier because you already have the component building blocks at hand. Very powerful and complex functionality can emerge from a relatively small number of simple building blocks. Of course, when you start writing a particular piece of code, you might not know exactly how long it's going to be. But once you've finished it, you can then take a look at that code and ask yourself questions like, what can I do to make this simpler? Can I take some of these repeating statements and put them into a function that I can use again and again? Can I chop this big program up into smaller pieces that then I could maybe reuse in the future? This whole process in computer science is called refactoring. In our community of practice, this is absolutely what we're aiming to do. As I'm currently the only university qualified computer scientist on the team, I'm going to try and help out as best as I can, and I'll be trying to impart some of the software engineering and solution architecture knowledge I've learned so that our community can write code where we can leverage our own previous code and that of other people in the community really efficiently. We can all grow together. That's the whole idea. So that's the end of this lesson. We've covered 6 important concepts about coding. In the second part of my coverage of coding essentials, we're going to cover some other important programming knowledge, namely variables and logical statements. And both of these are important in branching and looping.